Go ahead.
This is the Simulink model of the quadcopter. And as you can tell, it takes input from a joystick, which is actually this Xbox 360 controller, switches into some mode logic, and then goes into a command block, which takes the mode logic and the joystick positions and translates that into desired accelerations. And then there's a control allocation block, which takes those desired accelerations and turns that into basically actuator commands, which produce forces, which then go into the dynamics plant. And I'm just going to show you a quick simulation. Let me hit the play button, and here you can see the quadcopter centered in the middle. Currently it's not moving, but it's we have the moments of inertia and the masses and gravity and all of that figured into the model. And right now it's the PID controller, which is the main source of control. So for example, I give it some yaw and it will start turning, and then it stops turning because the yaw is a yaw rate command. So when I return the joystick to 0, it goes back to 0. And then there's the height command if I make it go up. But of course, the way I have it is I have it as a fixed axis to the center point of the quadcopter, so you can kind of see it going up the z-axis as I command an up position. And of course, there's a PID controller for the z, and it'll have a little bit of overshoot and then resettle. And then the one, which is a little bit more complicated, which we played around with, is the roll and then the pitch. And as you can tell, it works. Over here, this is one of our PID controllers, and as you can tell, there's the proportional, integral, and derivative gains. And essentially what we're working on is tuning these to be optimal for certain conditions. So if we want a certain overshoot or a certain settling time. And one of the ways we do that is we've set up a step input into the program, and this step input simulates the quadcopter traveling from 0 to 30 degrees along the roll axis, and we take a look at how long it takes to respawn, how much overshoot there is, and from that we can kind of judge how effective that PID setup is. So it's going to go for 15 seconds, so it'll take a few seconds. So we have the PID gains for those two axes, and we also have PID gains for the RP and Y, the roll, pitch, and yaw axes. And here are the results of our test. As you can tell here, this is the commanded 30 degrees. This is the initial 0 degrees, and of course there's some overshoot and some settling time, but within approximately 2 seconds, it's basically settled. And we're still working on this model, and hopefully within the next couple months we'll have something that we can publish in a professional journal.